Welcome to solverfy.
Here we have a reaction of HNO2 with KOH, which forms water and KNO2. If we're titrating 23.4 milliliters of 0.039 molar HNO2 with 0.0588 molar KOH, in order to get to the equivalence point, we're going to want to completely react the HNO2 without adding any excess KOH so that only water and KNO2 are present in the solution. So in order to do that, we have to have an equal number of moles of HNO2 and KOH, since there is a 1-to-1 ratio between the two. So first, let's calculate how many moles of HNO2 we have. Molarity is moles over liters. So our number of moles of HNO2 is equal to the molarity of HNO2, which is 0.0390 times the number of liters of HNO2, which is 0.0234. So we know we have 0.000913 moles of HNO2. That means we also need 0.000913 moles of KOH to completely react with the HNO2. So now with this information, we can solve for the volume of KOH we need to add. Using the same equation here, we have liters is equal to the number of moles over the molarity. So the number of liters of KOH we need is 0.000913 moles over 0.0588 molar. And this is equal to 0.0155 liters of KOH, or 15.5 milliliters of KOH. So we have the volume of KOH needed to reach the equivalence point. And now let's find the pH at the equivalence point. All that exists in solution at the equivalence point is KNO2 and water. So let's look at a reaction between these two. In solution, these ions will separate from each other, and so will these. And so potassium is what's called a spectator ion. So we can rewrite this equation without potassium. Now let's set up an ice table. Our first step is to figure out how much or what the concentration of NO2 minus is in the initial step. We don't have to worry about water since it's the liquid, and we don't use the liquids in our calculations. So we know that in order to reach the equivalence point, we reacted 0.000913 moles of HNO2 with the same number of moles of KOH. Since there is a 1-to-1 ratio of each of these with NO2 minus, we know that there will be the same amount of moles of the NO2 minus at the equivalence point. So we know we have 0.000913 moles of NO2 minus at the equivalence point. Now in terms of volume, we started with 23.4 milliliters of HNO2, and we added 15.5 milliliters of KOH. If we add those and convert to liters, we get a total volume of 0.0389 liters. This then gives us a molarity of 0.0235 molar NO2 minus. So now we finally have our initial concentration of NO2 minus, which can go in our ice table here. And our initial concentrations for the products are 0 molar for each of them. Our change is then some unknown X, so we react X NO2 minus, and we form X of each of the products. Then our equilibrium is just our initial plus our change. So for NO2 minus, 0.035 minus X. For each of the products, just X. Now we know that the Kb of NO2 minus is equal to the concentration of HNO2 times the concentration of OH minus over the concentration of NO2 minus. And we also know that Kw is equal to Ka times Kb. This is important because we can look up the Ka value of NO2 minus's conjugate acid, which is HNO2. We can look that up in the textbook. And the value of that is 7.1 times 10 to the negative fourth. So we can use this number here to convert to Kb, which we can then use in this equation here to solve for our values of X. So let's do that. Plugging in our Ka into this equation here, we get a Kb of 1.41 times 10 to the negative 11th. So 1.41 times 10 to the negative 11th is equal to our concentration of HNO2, which is X in our table, times our concentration of OH minus, which is also X, so we can just write this as X squared, divided by our concentration of NO2 minus, which is 0.0235 minus X. In order to make solving for X a little bit easier, let's make the assumption that X is so small that subtracting it from 0.0235 here is not going to make a difference. We can make this assumption as long as we check it at the end to make sure it was valid. So if we make that assumption, then we have 1.41 times 10 to the negative 11th is equal to X squared over 0.0235. Solving for X, we get that X is equal to 5.75 times 10 to the negative 7th. And this tells us that our assumption is valid since 0.0235 minus 5.75 times 10 to the negative 7th is still 0.0235 to 3 significant figures. If our assumption was invalid, we would have to go back and resolve this problem for X using the quadratic equation. But since our assumption was valid, we can just move on. Now that we have our value of X, we also have our value of the concentration of hydroxide at our equivalence point. That's because at our equivalence, at our equilibrium, we have X molar OH minus. And now we finally have enough information to solve for our pH. pH is equal to 14 minus POH, or 14 minus the negative log of the concentration of OH minus. Plugging in our concentration of hydroxide, which is equal to X, we get a final pH of 7.76. Titrating H2CO3 with KOH will result in two equivalence points because H2CO3 has two protons to lose. First, it will form HCO3-, which will then further react with KOH to form CO3-2-. So let's look at these reactions one at a time. First, we start with 17.3 milliliters of 0.13 molar H2CO3 and 0.0588 molar KOH. Here, just like in the last problem, we can multiply the molarity by the volume to get the number of moles. So if we multiply 0.130 by 0.0173, we get our number of moles of H2CO3, which is 0.00225. Here, now we know we need 0.00255 moles of KOH as well, since we have a 1-to-1 ratio of KOH and H2CO3 that react in our titration. And just like in the last problem again, we can solve for the volume of KOH needed. So we just divide this by our molarity. Here, 0.0588 to get a volume of 0.0382. Here, this is also equal to 38.2 milliliters. Here, now once we've added this much KOH, we are at our first equivalence point. So all we have in the solution is KHCO3 and water. So if we look at a reaction between the two, HCO3- is how it will exist in solution with water. Here on the right we have H2CO3 and OH-. Then from here we can set up our ice table. So first, how much HCO3- do we have initially? Well, we started our titration reaction with 0.00225 moles of H2CO3, which react with 0.00225 moles of KOH. And since there is a 1-to-1 ratio of each of these with HCO3-, we have the same amount of moles of HCO3- after the reaction once we get to the equivalence point. So we know we have 0.00225 moles of HCO3-, but now we need the concentration. So we divide this by our volume, which will be our original volume of H2CO3, which is 17.3 milliliters, plus our added volume of KOH, which we calculated to be 83.2 milliliters. Sorry, 38.2 milliliters. Here, this gives us a concentration of 0.0405 molar. So we can put that here, and we can ignore water again since it's a liquid. And our initial concentrations of each product is 0 molar. Our change is then some amount X of HCO3- is reacting to create X H2CO3 and X OH minus. So at equilibrium, we have 0.0405 minus X for our concentration of HCO3 minus, and X for each of our products. Now, really quickly, our Ka values for H2CO3. Ka1 is 4.5 times 10 to the negative 7th, and Ka2 is 4.7 times 10 to the negative 11th. Ka1 corresponds to the loss of the first proton, so equation 1, and Ka2 corresponds to the loss of the second proton, or the second equation here. Now, using Ka1, we can do the same process that we did here in the first problem. Here, using the value of Ka that we have for H2CO3, we can solve for the Kb of HCO3 minus, and we get 2.22 times 10 to the negative 8th. And we know that the Kb is equal to the concentration of the products. So the concentration of H2CO3 at equilibrium multiplied by the concentration of OH minus at equilibrium, which is X squared, divided by the concentration of HCO3 minus at equilibrium, which is 0.0405 minus X. Here, again, we can try making that assumption that X is so small it won't make a difference if it's here or not. And if we do that, we can solve for X and we get a value of 3 times 10 to the negative 5th, which tells us that our assumption is valid. So now we know our final concentration of OH minus, which we can use to solve for a pH. pH is equal to 14 minus the negative log of the concentration of our OH minus at equilibrium. So plugging in X for our concentration of OH minus here, we get a pH of 9.48. So that's our final pH for the first equivalence point. And now we have to repeat the whole process to find the volume of KOH required and pH for the second equivalence point. So as we know from before, we start this second part of the titration with 0.00225 moles of HCO3 minus. Again, there is a 1-to-1 ratio between HCO3 minus and KOH, so we're going to need an equal number of moles of KOH to react completely with the HCO3 minus to reach the equivalence point. So 0.00225 moles of KOH over our molarity of KOH, which is 0.0558, and we get the same amount as we did last time. So this is the volume of KOH we'll need to add to the titration after reaching the first equivalence point. So if we want a total volume of KOH, then we need to add from the very beginning to get to the second equivalence point. It will be the addition between both of these, and we get a total volume of 76.4 milliliters of KOH. So again, at this point, we are at the equivalence point, which means we only have KCO3 minus and H2O present in the solution. So we can set up another equation here. CO3 2 minus from the KCO3 minus plus the water partially dissociates to HCO3 minus and OH minus, both in the aqueous phase. And again, we make an ice table. Here, and for our initial concentration of CO3 2-, we have reacted 0.00225 moles of HCO3- to form the same number of moles of CO3 2-. And our volume is going to be our original 17.3 milliliters of H2CO3 plus our total addition of KOH, which is 76.4 milliliters. This gives us a total concentration of 0.024. So we can write that down here, ignoring water again because it's a liquid. And our initial concentrations for the products is again 0 molar. Our change is again minus x on the left and plus x on the right. So our equilibrium is 0.024 minus x for CO3 2-, and x for each of the products. From our value of Ka2 for H2CO3, we can calculate Kb for CO3 2- to be 2.13 times 10 to the negative 4th. And we know this is equal to x squared from our products divided by 0.024 minus x from our reactants. Here, if we make our small x assumption and we solve for x, we get a value of 0.00226, which actually does not validate our assumption, so we have to do it the long way. Here, rearranging this equation, we get the expression x squared plus 2.13 times 10 to the negative 4th times x minus 4.81 times 10 to the negative 7th equals 0. Here, using the quadratic equation, we can solve this to get x equals 5.49 times 10 to the negative 4th. Here, any negative values you get when solving for x, you can just ignore since we know we need a positive concentration for our products here. And this here should say HCO3-. Alright, now we can solve for our pH the same way we did over here. And we get a final pH value of 10.7.